essentially what we were doing, I'll start again and say, is we're going to look at this section today. It's called Green's theorem. And Green's theorem states that this line integral, so a line integral is typically written, one of its ways is to write that. That little circle means it's a closed loop. What that means is that the curve C isn't like starts here and then like finishes up here, which it typically does. It starts and you go round it anti-clockwise and you go back to the beginning. So that's what a closed loop means. And according to Green's theorem, if you do a line integral over a closed loop, and the general version of that line integral was P dx and Q dy, where P and Q are functions of x and y, then it's very often easier to calculate that line integral in terms of a double integral. And the region D is basically that same guy, but the bit inside. And that's the partial derivative of Q with respect to X, and that's the partial derivative of P with respect to Y. And this double integral is using dx dy. So that's kind of where we got to. And over here, I have an example of a question. Let me try and adjust this a little bit more. There we go. And in this particular question, this is a version of question 1. Actually, it looks to me like it is question 1. This line integral over the closed loop C of xy dx plus x squared y cubed dy. Now C, this guy here, is a triangle from the origin to this point to that point, and obviously back to the origin, because it has to be closed. So it's not like two sides, you join the third side up. And it's you're going to go around it in an anti-clockwise direction. And that's kind of where we'd got to before my dogs decided to disconnect all the cables. So identify P and Q. So this guy is P. This guy is Q. And the region D will be this triangle. So if I draw a little version of what this triangle looks like, it's the origin. It's 1, 0, and then it's 1, 4. And then you come back home again. And we're going to go round it in that direction. So this shaded area here is what we call the region D. So this guy here is region D. Basically, I'm setting up all the pieces that we need. So this, it's called a line integral over the closed loop C, where that guy xy with respect to dx and this bit with respect to dy turns into a double integral over the region D, which is this guy. The partial derivative of x squared y cubed, because that's Q, plus the partial derivative with respect to y of this guy, integrated with respect to that double integral, dx dy. I may change the order of them. We'll find out in a minute whether I should. And this region here, this region D, we need to find out what its limits of integration is that we create that. So what I would probably do here is think of a typical rectangle, that guy there. And if I do it this way, x will go from 0 to 1. So that tells me x is going to go from 0 to 1. And y is going to go from the bottom, which is clearly 0, to the top, which is that straight line. And this guy here has coordinates 1, 4. So the straight line we're talking about is essentially this purple line here, right? And so I need to find what its equation is. Well, it passes through the origin. And if you use that point, you can see that it's 4 by 1. So its slope is 4. So it's going to be from there to there. Okay. Got a chat. Let's see what it is. Okay. So are you comfortable right now with how I created the limits of integration for this region based on the fact it's a triangle and that we're going to go around it in an anti-clockwise direction? I'll take a thumbs up if you're good. I'll take a thumbs down if you're not so sure. And I don't have any response, which could be an issue with you can't hear me. Can you lot hear me? Okay, let's try it as a comment then. Okay, we got a thumbs up. It's good, right? So x goes from 0 to 1. Y goes from 0 to 4x. If you do the partial derivative of this term with respect to x, you get 2x y cubed plus the partial derivative of this with respect to y gets you x. And I think based on the fact that this should go first, I'll change the order to dy dx. Nothing else needs to change. And the reason I'm doing that is because this limit of integration has to be done first. So I need to do dy, and then the x's can come last. So I've got the integral from x equals 0 to x equals 1. And I'm going to integrate this guy with respect to y. So you add 1 to the power and you divide by the new power. You get that guy. And if you integrate x, which is essentially a constant, but with respect to y, you get that. You then evaluate it at y equals 0 and y equals 4x dx. Okay, if you plug in 4x here, you get 1/2 x, 4x to the power of 4, plus x times 4x. Take away a whole load of zeros. So it's going to be x equals 0 to x equals 1. It's a messy thing, but I'll try and do it. 4 to the power of 4 is a ridiculously big number. Of course, I won't have my calculator with me. So I'm going to call it 4 to the power of 4 over 2 x to the 5 plus 4x squared dx. Right, 4 to the power of 4 is what? 16. Oh, it's 256. 128. Oh, got it. So it's going to be the integral from 0 to 1 of 128x to the 5 plus 4x squared dx. And that guy. Oh, darn it. Well, I caught it in time. The formula is minus. That's a 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 minus. Okay. So it's the first guy, take away the second guy, which I actually wrote but didn't copy. If you integrate this and then divide by the new power, you'll get x to the 6 over 6. You'll get x cubed over 3. You can then evaluate it from 0 to 1. And evidently, as strange as it may seem, you get the answer 20. Go figure. That's what it says here at least. So that's basically the process. What you're going to get is you're going to be asked to do this line integral. You're going to use this theorem that allows you to turn it into a double integral. You're going to figure out what the region is and set up the limits of integration that match this fella. And then you're going to differentiate this guy with respect to x and this guy with respect to y. I think we're good. Double check I got it the right way around. Yes, I did. So have you noticed there's a kind of crossover thing? This guy goes here and that guy goes here. So it's kind of back to front, but that's the way it works. Now, if the only difference that they had done to this was not go around this triangular region in the correct or positive anti-clockwise direction, but they went round it the other way, right, this way here, the only essential difference would be that the answer would be the negative of what it is. So if this is 20, the other direction would get you negative 20. Okay, any questions about our first one? How we can use what's called Green's theorem, which is a way to take a line integral and convert it into a double integral that has the same numerical value as the line integral. Are we good? I'll take a thumbs up. Okay. A lot of the questions that we're going to be doing is basically going to be going through this process. Right. So I'm going to start but not finish question 2. So question 2 has got this guy, and it's y e to the x dx plus 2e to the x dy. So that makes this guy p, makes this guy q. And the region that we are going to do this, region C, is going to be a rectangle, and it's 0, 0 to 5, 0 to 5, 6 to back to 0, 6, right? And then back home after that. So see what that region looks like in the XY plane. You go from 0, 0 to 5, 0, which is that. 5, 0 to 5, 6, which would be here. 5, 6 to 0, 6, which would be here. And then back home. So that there represents our region D. Now, the limits of integration of a rectangle are the easiest to do, so I'll set those limits up right now. X goes from 0 to 5, and y goes from 0 to 6. And according to Green's theorem, this line integral can be converted into this double integral. So let's see what we get. It's going to be x equals 0 to 5, y equals 0 to 6. Then it's going to be the derivative p with respect. There we go. Q with respect to x. So that's this guy. Take away p, which is this guy, with respect to y. And in this case, it's going to be a dy dx. And so it's going to be x equals 0 to 5. Y goes from 0 to 6. If you differentiate this guy with respect to x, you get 2e to the x. If you differentiate this guy with respect to y, you will get, e to the x dy dx. Oh, I didn't know that was going to happen. Okay. I can do a little bit more. Because those are the same guy. You get that? Okay, now you integrate that term with respect to y, you just get exy. So I suspect you're just going to get 6e to the x, which you then integrate with x, which will also be 6e to the x, and then you plug in a 5 and a 0, and you are good to go. That question was actually scarily nice. Okay, the next region they're going to deal with is question 3, but I'm not going to deal with any of the integration part. We'll let you deal with that. I'm just going to deal with the line integral, which goes through these 3 points. So it goes to the origin, then it goes to here, then it goes up to this point here, which is 1, 6, and then it goes across. Oh wait, it's a triangle. Doesn't go across, it goes to here. So this region, that's D. So I would probably go vertical again. And that way X can take the limits from 0 to 1. Y, well, it's going to be on the bottom, so that's 0. And it's going to get to there, and that straight line passes through the point 1, 6, so that makes it y equals 6x. So there is your region D. And basically you just find a derivative of this guy here with respect to x, subtract the derivative with respect to y of this guy. So you notice it's a PQ, QP kind of thing. Easy to get them mixed up. So far, so good. Now, it is possible that you do a question, and I'm pretty sure at least one time this is going to happen, where this expression equals 0. And don't freak out when it does, because it means that this line integral over the closed loop C of P dx plus Q dy is 0. Because if you think about it, if this is 0, the double integral of 0 will get you 0 regardless of the limits of integration. And that's because if this thing is a conservative field, then all you need to know is the start position and the finish position. And if you think of a loop, the start and the finish are going to be the same point. So you end up with the value of the function at A, take away the value of the function at B, being the same two things. And so something take away itself is 0. So if you have a conservative field, which basically means dq by dx is equal to dp by dy. If you have a conservative field, then this integral, this line integral, will always be 0. So that's kind of helpful. I'm not saying this one is, but it might be. And that's it. So, any questions? Because this is actually, both these sections are being quite short, which is, I guess, nice. Do you have any questions before we go on to our next version of this? Okay, let's look at 4. In question 4, we're going to be finding that line integral. It's 3y plus 7e to the square root of x dx plus 8x plus 3 cosines of y squared and dy. The region C is described as the region bounded by the curves y equals x squared and x equals y squared. If I draw a little picture of what that looks like, that's what y equals x squared looks like. And if you rearrange this, it's actually just the square root of y, or the square root of x. So you're actually talking about that little area there from 0 to 1. So that's our region D in there. Well, this guy is P, all of this. This guy is Q, all of this. I'm going to do a double integral. Now in this case, I'm going to do it vertical again. And so the x's are going to be the easy one. They're going to go from 0 to 1. And the y's are going to go from square root of x squared, I should say. The bottom one's x squared. So that's y equals x squared to y equals square root of x. And then we should be differentiating with respect to x, this guy. And here's some good news. I'll just call it Q. And take away, differentiate with respect to y, P. And then I can do, well, it's going to be dy dx again. So take this just a little bit further. Superficially, these terms, especially that one, and probably also that one, are extremely ugly looking, and you really wouldn't want to do an integral with them. So let's see why it's good news. This is Q. If you differentiate this with respect to x, all you get is 8, because 3 cosine of y squared is considered a constant, and the derivative of a constant is 0. I got somebody in the chat. Oh, doing good. Okay. Now, take away, if you differentiate this guy with respect to y, that is considered a constant, so its derivative is 0, and all you get is 3. And I'm going to do, well, I'll take it one more line. Now, you can't separate these integrals, so you have to do y first, which is this bit. Get the answer and then do the integral with respect to x. But since that's a number, its integral is just going to be 5y, and that'll be one of your guys, and that'll be yours. So you basically just end up with various powers of x being integrated when you get to the next level. Are we good with that one? Yeah, okay. Now the next one is question 5. I think I'll have to take this a little bit further along. This is at least my version. Oh, they technically should have that on all of them, which just means that it's a closed loop integral. But it looks like WebAssign sometimes does it, but most of the time doesn't. For what reason, I cannot think. Because it is a closed loop. If you're going to use a notation, either use it all the time or don't use it at all. Okay, so that's the guy we're going to integrate. And C is going to be a circle. X squared plus y squared plus 4. So I even know how to draw it. And it's described as positively orientated curve. And a positive orientated curve means you go anti-clockwise. So that's good news. Now, this piece here is P. Right? This piece here is Q. This region, which is basically well, a circle, right? Because the bit inside is going to be a region D, is a circle. And I think it would be nice to describe this circle by just doing polar. So that's going to say equals. So its radius is 2, and it's the whole circle. So it's that guy. And that's fine. Basically just changing the variables a little bit. So it's going to be a double integral over this region D, the partial derivative with respect to x of q, take away the partial derivative with respect to y of p, and I'll just call it dx dy. I can switch that order later if I need to. I'm just going to leave these as d right now. If you differentiate this guy here with respect to x, you get negative 15x squared. Take away, and if you differentiate this guy with respect to y, you get take away 15y squared. And right now we're still on dx dy. Are we good? Any issues, or does that seem reasonable? Okay. Right, let's move on. Trying to do this circle in the limits of integration in x's and y's is not a good idea, which is why I'm doing this though. So when you do a conversion from x, y into r and theta, you remember you get an extra r, so it's r dr d theta. So these guys here are now going to be r dr d theta. This guy here, I think I'll do the working in boxes. This guy here, this expression, if I pull out negative 15 as a common factor, I get that guy. And hopefully you can recognize that that guy is r squared. So this piece here, I'll put little brackets around it for emphasis, is that guy. Now the region D is described by these fellas. So I'm going to do r equals 0 to r equals 2, and theta equals 0 to theta equals 2 pi. And then I'll do a little tidying up. And what we essentially get is negative 15r cubed. And since I've decided for no particular reason to do the theta, that would be the correct order. Now, since the limits of integration are all numbers, and this expression doesn't even have a theta in it, we can change it into two separate integrals. And you can decide whether this guy gets the negative 15 or you make this guy get the negative 15. It won't change your results. And you are good to go. In fact, couldn't you probably just pick it up and stick it outside integral? And you finish and you're good to go. So in general, if the region, right, if this curve makes a circle or half a circle, in this case it was a full circle, I suggest strongly that you go polar. So in other words, use r and theta as your variables. Whatever these expressions are, you would have to convert them into r's and thetas. So if there's an x somewhere, you would call it r cos theta. If there's a y, you'd call it r sin theta, and so forth. The dx by dy piece gets replaced by its standard r d theta. And whatever expression this turns out to be, hopefully it's something nice, convert each of the x's and y's using, and I didn't actually put that in, so I'll put it here. If you have an x that you need to take care of, just an x on its own, it's that guy. If you have a y to take care of, it's that guy. We didn't need this in this question because basically if you pull out negative 15 here, you get x squared plus y squared, which means, boom, you're good to go. Okay, how are we doing on this one? We getting a thumbs up? Good. Okay. The next region, I'll take it about halfway, I think. You have a region that's described by a picture that looks something like this. This outer circle, well, quarter of a circle, is x squared plus y squared equals 16. And this inside curve is x squared plus y squared equals 4. And this guy here obviously is 2 then, and this is 4, and this is 2, and this is 4. So the region D that we're talking about is this region here. So I need to set up what that region would look like. And again, I'm going to use polar. Well, if you take a normal projection line, any one of these, you're looking at an inside circle of radius 2 and an outside circle of radius 4. And if you think starting at the x-axis and rotating, you're only doing 1/4 of a circle. So theta goes from 0 to pi upon 2. So that's my limits of integration. My dx dy will get replaced by r dr d theta, which is good. And they are writing your integral down, your line integral, excuse me, using that notation. But they also, thankfully, write it down. Excuse me, I got a frog in the throat. 3 plus e to the x squared dx plus the inverse tan of y plus 3x squared dy. So this guy is P, this guy is Q. I know that it's going to be a double integral over this region D. It's going to be the partial derivative with respect to x of Q, take away the partial derivative with respect to y of P. And right now, I'll just call it dx dy, but I may change that order. If you differentiate this guy with respect to x, he doesn't matter, so you get 6x. And if you differentiate this guy with respect to y, you get even less. And I'll call it dx dy for a little while longer. Okay, let's start turning things into polar. It's going to be r equals 2 to r equals 4. It's going to be theta equals 0 to theta equals pi upon 2. This expression here just ends up being 6x. And the dx dy gets replaced by r dr d theta. Now, the only piece that I haven't converted into polar is that x. So, to save me rewriting everything again, can we just turn it into r cos theta times r dr d theta, which now, when we combine things, becomes 6rr, which is what 6r squared cosine theta d theta dr. Now, do you notice that everybody is numbers? The limits of integration are numbers. Did you also notice that the expression that we're going to integrate are two things multiplied? We can separate them. So the last piece of the puzzle would be r equals 0 to r equals 4, 6r squared, times theta equals 0 to theta equals pi upon 2 of 1 d theta. And then you finish it and you get the details that you need. Any problems? Are we good? We're good. Okay. All right. So the next question, well, it's a bit long, but let's set it up. Take this about halfway, I think. We're going to find this guy. I would put that in just all the time. And they're writing it down initially in that format. But essentially, the guy that you're dealing with, the F that you're dealing with, right, is Y. Oh, let me show you what it's written like before I go anywhere. They describe F in this format here, which is Y cos X, take away XY sin X, comma, but I don't have enough room to squeeze it over here. Or maybe I will, comma, XY plus X cosine X. Now, that guy is P, that guy is Q. They also tell us what C is, and they say it's a triangle. And I'm going to just draw it. It starts off at the origin, and it goes to 0, 6, which is here. It then goes to 2, 0, which is here. And then it comes back home to here. So this is the region D. Do you notice that its orientation is, for want of a better word, the wrong way? It's being orientated this way when shouldn't it be anti-clockwise? But this is in fact, oh, wait a minute, orientation. Oh yeah, this is clockwise. For some reason my brain wasn't functioning. So that's the wrong, well, not say not wrong, but that's not the typical direction. So what that means is that our answer has to be fixed. And the easiest way to fix that is to stick a negative, because that's all it'll do. And then you can just do it the way you always do it. So let's set up limits of integration for this fella. X is going to go from 0 to 2, and Y is going to go from 0 to that guy. Now that straight line has a slope of -3, right? And it passes through 6. So that's the equation of this line here. So what was I going to write here? Oh. So we're going to do a double integral over this region here, which I'm just calling D right now. The minus is to account for the orientation being clockwise. And then we are going to do, I don't know where that came from, P, and now I know where it came from. dq by dx, take away dp by dy, and then we'll do a dx dy. Let's separate all that stuff out. So our integral is going to be from x equals 0 to 2, y is going to go from 0 to this straight line, which is 6 take away 3x. If you differentiate this expression with respect to x, let's check that, p and q. Something confusing me here. Check. Okay. So I'm going to be differentiating this guy here. I'm looking at their solution and it's not matching mine. What on earth have we done? What have I done? Oh, I know what they've done. Okay. F is already written in the form that we need, which is these two guys. So when I'm differentiating with the two guys, I'm basically just going to be differentiating this guy with respect to y, right, and this guy with respect to x. So why the heck is that not working? Did I write something down wrong? Let's check. It's y cosine x, check. Take away that guy, check. And then it's this guy, check. And that guy, check. I didn't do that wrong. So that guy, when you differentiate, should just get you. Doesn't get you. It's definitely too late in the day. Their solution does not. Oh, okay. This is Q. If I differentiate this with respect to x, okay, then I will get a y minus an x sine x and plus a cosine x. And the reason that I'm going to get three terms out of this guy is differentiate this guy with respect to x, you get y. If you differentiate this guy with respect to x, you use a product rule, and that's what you get. Okay, now I'm happy. Okay, take away. If you differentiate this guy with respect to y, you are going to get, what are you going to get? You're going to get take away. This guy is just going to be cosine x. This guy is going to be take away x sine x. That's good. And it looks like it's going to be a dy first and a di second. So let's check that out. If you differentiate this guy with respect to x, you get these three terms. If you differentiate this ugly guy with respect to y, you only get these two terms. We get x equals 0 to 2, y equals 0 to 6 take away 3x. And let's see what we've got. I have a y, I have a take away that guy, I have an add that guy. I then have take away a cosine x, and then take away a take away is an add x sine x, and dy dx. And something remarkably nice happens. Dead. So all we get is from x equals 0 to x equals 2, from y equals 0 to y equals 6 take away 3x, and the only guy that's left alive is a y. How pretty is that? And you can finish that off. Evidently, according to whoever saying it's -12. Right, I get a little bit distracted by the P's and Q's in the form that they've written it. I much prefer them to write it as, you know, this guy dx plus this guy dy. It just, my brain seems to function better when it's written in that format. Any questions about 7? Because it did take me a little while to finally figure out what the heck was going on. We good? We're good. Okay. Well, we're well by halfway. So looks like this week has got a lot less going on, which is fine. So it's a version of question 8. They're asking us to find that guy. But they give us the information in the way that I would want it to be written, or at least in a way I can identify who is who. That's this guy. Plus this guy. So identify him as P, identify him as Q. That'll be good. Now, what does the C look like? Well, according to their instructions, it's the cosine x going from the point -pi/0 to the point pi/2, 0. And then a line segment, which just means a bit of a line. And the line segment goes from pi/2, 0 to -pi/2, 0. So let's see if I can sketch what that looks like. If you do -pi/2 and you do +pi/2, then the cosine function looks like that. And so you're going that way. And then pi/2 to here basically just means you come back that way. So this is the region D. Now I want to set up its limits of integration. So if we take a random vertical rectangle, x was going to go from -pi/2 to pi/2. And that guy is 0. And that guy is cosine of x. Okay, so there's our limits of integration. That's our region D. So we're going to do a double integral over the region D. The partial derivative of q with respect to x. Take away the partial derivative of p with respect to y. And looking at what I have here, it's going to be a dy dx orientation. Now we know the limits of integration. You always do the numbers if there's only one number on the outside. And you do the y's. In this case, those guys. And you differentiate this guy with respect to x. All you get is 2x. And if you take away, if you do the derivative of this guy with respect to y, all you get is 2y. And then you're going to go dy dx. So that's the limits set up, and that is this expression written down. Let's see what we can get. I think I'll take it one line further. If you do this guy with respect to y, you get 2xy, and if you do this guy, you get -y². And you're going to evaluate it from 0 to cosine x. What else can I do? Well, that's going to be the integral from -pi/2 to +pi/2, 2x cosine x, take away cosine squared x minus a whole load of zeros. And we get to there. This is where I'm going to stop. This guy here is going to have to be integrated, and it's going to have to be done using integration by parts. So to remind you how that works, it's f of x, g of x, take with the integral of f dashed x, g of x dx, where capital G of x means the integral of this guy and f dash means its derivative. And this guy, any suggestions how I integrate cos squared x? Any ideas? How would you integrate cos squared x? It's a Calc 2 issue. Any takers? Let's check it. Okay, and the formula then is, well, since that's a negative, you're going to get a negative. It's 1/2 1 plus the cosine of 2x and dx. And that's going to be negative 1/2, negative 1/2 cosine 2x. So that's the guy you're going to have to integrate and finish it off. And evidently, the answer ends up being very nice. Okay, I think we've got 3 more and we're finished. Just set up 9, I won't do anywhere. I'm just curious what's going on here. No, that one's not what I thought it was. Nine had more algebra in it than I really expected it to be. Basically, you do it using the data too that I don't think you're aware of. Okay, so the guy that called 9 won't exist anymore, and at least it won't once I get into it. So the new guy, number 9, is going to find the work done. So you have a force vector called this guy, and it happens to be equal to x plus y, comma, xy squared. And you're going to find the work done in moving the particle origin from the origin, right? So it's from the origin to the point 40, to the point 04, and then back to the origin. Okay, so I now know what the region is. Now, if you want to find the work done, it's actually that guy over the curve C, which we will turn into its typical equivalent double integral. And you are P and you are Q. Okay, let's build all the pieces. This guy here starts at the origin. It then goes to 40, It then goes to 0, 4. And then it comes back down again. Oh, it's a little triangle. And so that region is D. And I'm going to build its limits of integration. Again, X seems to be the most natural. And the Y is from the bottom, which is 0. And the top is a straight line. And that straight line happens to eventually be the equation 4 minus x, but you can check that. So it's going to be the integral from x equals 0 to x equals 4. The integral from y equals 0 to 4 minus x, which I'm reasonably happy with. And now I need to find the derivative of this guy with respect to x. Well, the derivative of this guy with respect to x is y squared. Take away the derivative of this guy with respect to y. So I probably should have written it like that. And if you do that one, he gets you 0, right, with respect to y, and this guy gets you an x. So it looks like that's the two guys we've got. And then it's a dy dx. And dot, 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 dot. I think you can finish that yourself. According to the answer I have, it's 32/3. Okay. So well, first, are we okay with that one? Any questions? Okay. You are allowed to ask questions. Okay. I think we've got just 2 more questions to go. So, as I say, this is a very quick question. This is 10. Okay. A particle starts at the origin. Okay. So it starts at the origin. Let's draw it. Starts there. It then moves along the x-axis to 3, 0. Check. Then along the quarter circle, x squared plus y squared. So it goes from 0, 0 to 3, 0 to quarter of a circle. So I'm assuming that that's a quarter of the circle. Essentially just means you do that, which means that's 3. And then back home. Okay, that would have been easier if they just gave you the picture, but they didn't. So there is our region D. Now, the function that we're going to do this operation on is a force field. And it's the sine of x, comma, and then a big long expression, the sine of y plus xy squared plus 1/3 x cubed. So that little guy there is p, and all of that guy is q. Now, since the region D is part of a circle, that makes me think it would be a good idea to rearrange this question in terms of polar. So here goes. If you want to draw this region in terms of polar, you're going to do r is 0 to 3, and theta is going to be 0 to pi upon 2. And now I have the region D in polar. Let's do this piece here in terms of x and y, and then convert it to polar after that. So we're going to do a double integral over this region D. It's going to be the derivative with respect to x of q, which is this guy. Take away the derivative with respect to y of p, which is this guy. And right now it's a dx dy, but that'll change. Well, if you differentiate this expression here with respect to x. Let's see what you get. Nothing, y squared, x squared. Okay. So that's this piece. Take away. If you differentiate this guy with respect to y, you get 0 dx dy. So we have a double integral. Oh, I think it's time to turn into polar. The polar is going to go 0 to 3. The theta is going to go 0 to pi upon 2. X squared plus y squared is just r squared. Dx dy gets replaced by r dr d theta. If you remember, dx dy is r dr d theta. And so we're pretty much done. It's going to be 0 to 3 of r cubed and 0 to pi upon 2 of 1. Dot, dot, dot. Evidently, you get 81/8 pi. Are we good? Right. Whenever the region that they're talking about is a circle or a piece of a circle, you should think about going polar. It's just going to make the calculations so much easier to deal with. If, however, the regions are rectangles, triangles, squares, then keep the x's and y's because that's a much better format. Okay. Now, question 12 is a little bit weird. So here we go. It says use the following formulas. So A is this guy. It's also the negative of this guy. It's also 1/2 this guy. And A they're talking about is the area of a cycloid. A cycloid is, you know, it's one of those kind of shapes that go like that. It could be much more petal-like, especially if I'm trying to draw it. And this cycloid is given in its parametric form as t take away sine t, and y is going to be 1 take away cosine t. And since it's a complete cycloid, it's going to be a 0 to 2 pi. Okay, now you can pick any one of these three guys and they will all give you the area of this shape. Right, let's say it's this shape. Does anybody have a preference? I have a preference, so hopefully you'll pick the one I pick. But which one of these three would you pick if you wanted to make your life easy? 1, 2, or 3? Which should you pick? Any takers? I would pick this one. All of them work. I just want to pick the one with the least amount of work. So it's going to be the integral from t equals 0 to d equals 2 pi. Right now I'm going to write it as x dy. Just right now. It's going to be the integral from 0 to 2 pi. Instead of x, I'm going to use this guy. And I'm going to use this fella to figure out what dy is. Well, if you differentiate y with respect to t, you get nothing minus a minus, you get a sine t. And so dy can be replaced by a sine t dt. So times sine t dt. And so our integral now becomes 0 to 2 pi t sine t, take away sine squared t dt. And we came across this situation, this integral situation before. That guy is going to be integration by parts. Right? And you're going to make this f, you're going to make this guy g. And this guy is going to be, well, I think the last time it was cos squared, wasn't it? And this one is going to be turned into 1/2, 1 minus the cosine 2t. And then tidy it up a little bit, and you integrate it. And that is us finished.